These are the notes for 3.4 on Monday night. All you need to do is take them and then go in and take a Schoology quiz where I reference them in about 7 questions. So yesterday we were talking about curvature of a function and how that's determined by finding its second derivative. And anywhere the second derivative is positive, that means we are concave up, like making a cup or holding water. When the second derivative is negative, concave down, or shedding water. So knowing where a function changes from concave up to concave down is an important skill to have. We say that any x value in the domain of a function is an inflection value if the function changes from concave up to concave down or vice versa. So really what an inflection value often will look like is that spot on the graph where you were holding water and concave up, but then you took a turn and started to be concave down. And that point right there, the x-coordinate of it is called the inflection value, and the point itself is called the inflection point. And usually you're asked for the inflection point, which means the location of the point, x comma y, or in this case we're calling it p comma f of p. But really what's happening is it's the spot where we go from concave up, which means we had a positive second derivative, to concave down, or had a negative second derivative. If we could find where that change occurs in the domain of f, we have our inflection points. So it's important to note that a graph can also change its concavity at a discontinuity. So we always have to watch out for our discontinuities. Remember, those occur where f is not defined, either because there's a hole there, or more often than not, because there's an asymptote there. So I've got 4 graphs right here. The first 2 have concavity changes from concave down to concave up at P, so we say that is an inflection value, or the point P comma f of P is an inflection point. Same here, concave up or has the curvature of a cup, and then concave down at a point that is defined on the function. So we call that an inflection value. Note that that inflection value is occurring at the cusp. So this original function, we would have had no problems with f. But when we took f prime, there would have been a spot where the denominator was 0. Remember, f having a denominator of 0 indicates asymptotes, sometimes holes. F prime having a denominator of 0 supplies us with the location of a cusp or sometimes a vertical tangent. So right here, we've got a function that does not have an inflection point. And the reason this one does not have an inflection point is because it was concave up and then continued to be concave up. There was no change in sign of the second derivative. The second derivative is positive. It's holding water and holding water. And so there was no change in the second derivative. Again, in order for you to have an inflection point, there has to be a change in the sign or a change in curvature at a point that is defined. So be very careful. For example, your sign line on this is going to show that there's concave down, so you would add negative second derivatives, and concave up, so positive first derivatives, but we cannot call that an inflection point because there's an asymptote there, or the function is not defined there, or we could say because x is not in the domain of f. So we've got to watch all those fine details. So the formal definition of an inflection value is, whoops, sorry, I've got a issue on my smartboard. Just a second, I'm going to hit don't send and see if I can, okay, looks like we're good. So a possible inflection value of f of x is an x value in the domain, so again, that was this issue, such that the second derivative is 0 or does not exist. Those are called possible inflection values. So that's kind of like our critical points. but they're critical values of the second derivative. The graph of a function can change its concavity at either a possible inflection value or a discontinuity. Again, right here, we had a change in concavity at a discontinuity. So let's talk about how we test our intervals. So the first thing we do is we find any issues with f itself, and we make a sign line, and we say that on f, sorry, there's so many announcements going on right here, it's driving me nuts. Anyway, I'm going to wait for him to be done talking. You probably can't hear it because I have a headset on, but there's somebody talking on the announcements. All right, that announcement's now done. So first thing we do when we're testing for concavity, and when you see concavity, you should think it's all about the second derivative. And I'm going to repeat something. When we are asked questions about critical points, about increasing or decreasing, and don't put this in your notes, or about relative extrema, maxes and mins, these are all about f prime. When we are asked questions about concavity or inflection points, which are changes in concavity, those are questions all about f double prime. So when I am looking at the concavity of a function, I make a sign line for the second derivative. I find any discontinuities and I put them on my sign line. So maybe at 2 there was an asymptote, and I like to put an infinity over it so I know this is not a possible inflection point. It can be where curvature changes, so I need to have it on my chart, but it won't be an inflection value. Then I identify all possible inflection values, places where the concavity can change that are in the domain, by setting the derivative equal to 0 or does not exist. This is second derivative, sorry. So keep in mind, changes in concavity can occur at discontinuities or anywhere the second derivative is 0 or does not exist. So let's suppose the second derivative was 0 over here at 5. And let's suppose the second derivative didn't exist over here at 7. And instead of putting infinity on here, I'm going to write d and e, because that means there's not an asymptote there. There's an issue. Then I make a sign chart, and I test all these intervals in the second derivative. And suppose it went plus, minus, plus, plus. This is what the second derivative is. So what it tells me with the function is it was concave up. Then there was an asymptote, and it was concave down. This is not an inflection value, but it did split up my concavity, so it's necessary. Then it was concave down. The second derivative was 0, and concave up. This right here is an inflection point because the concavity changed. 5 was a possible inflection value because its second derivative was 0. Now it's definitively an inflection point because there was a sign change there. Then what happened is I was concave up, had an issue, and was still concave up. So what that means is I had a cusp there. But you don't really need to know that. Really, what you need to get out of this is that when you are asked questions about concavity or about inflection points, you need to take the second derivative and analyze its signs. You need to split up the sign chart by finding all your asymptotes, and then anywhere the second derivative is 0 or does not exist, and then you do a sign line. Anywhere there is a change in concavity at a point that is defined, not an asymptote, you have an inflection point. So let's go to the next page. On the top of here, I have a graph. So let's find all the possible inflection values. That's anywhere where it appears that the concavity is changing sign. So let's go take a look at this. I have possible inflection values at B. It appears like it's going from concave down to concave up. At C, concave up to concave down. At D, I appear to have a change in concavity. E would be a possible inflection value. And then H as well. These are all places that appear to have a change in concavity. So let's say at each one, determine if there's an inflection value. Well, let's determine at B, it was going from concave up to concave down. So B is. At C, it's concave up and then concave down. So C is. At D, it's concave down, shedding water, and then concave up, holding water. So D is also an inflection value. At E, the answer would be no, because if I ran a sign chart on there, there would not be any sign change. There's a curvature issue, but it's not a sign change in the curvature. So it's possible, but this would have had a second derivative positive, and then I'm still holding water. So it would have appeared on my sign chart mathematically, but there would have been a plus on both sides. And then at H, although I'm going from concave up to concave down, H was not defined there, so there's a hole. So I can't say that it's an inflection point when there's no point there. So that actually will never happen mathematically, but whatever, it's good to read it off the graph, I suppose. So when it says to list the open intervals in which the graph of F is concave up, I just find everywhere where it's holding water. And that would be from B to C. That would be from D to E, and that should be a union, sorry. And then where else do I appear to be holding water or having a concave up graph? And that would be from E to H. I'm not going to do concave down, you get it. All right. So then it says, just like the first derivative line chart can be used to tell me everything about increasing and decreasing critical values, local extrema. The second derivative number line chart is to use to find concavity and inflection points. And I'm stressing that a ton because I do not want you to launch into the wrong test. So one more time. First derivative analysis on a sign chart tells us where functions are increasing and decreasing. They increase or decrease and have a change in that at what we call critical values. Critical values also can become relative extrema, but those are all questions answered by a first derivative sign test. A second derivative sign test tells us everything about concavity and curvature and where that changes. So any question about concavity or inflection points is a second derivative question. So some things to notice. Not every possible inflection value is an actual inflection value. We need to have a sign change at a point that is defined, so not an asymptote. Concavity can change at a discontinuity, like at a vertical asymptote, but that won't be an inflection point. It needs to be considered because you can be concave up on one side of an asymptote and concave down at the other, but that doesn't mean, despite the sign change, that you have an inflection point because we have to, again, be defined there. To find all of these possible inflection values, we set the second derivative equal to 0, and we find also where it's undefined because, again, those give us our cuspies. All right, and then we make our chart on a sign line. All right, and we find F prime double at all those places, at any discontinuity in the original function, at any discontinuity in the derivative or the second derivative, which gives us our cusps and stuff, and at any true second derivatives that are 0. And then we do a test. And we find which one of those are actually inflection points. This place, because it went from concave down to concave up, no, because there's no change in concavity right here. Even though there's a change in concavity, it's at an asymptote, so no. And this would be yes. This would be like the cusp situation up, it was on the other page, I think, where we have a cusp right here, where it's going from concave down to concave up. All right, so an example, and then we'll be done. Finding the inflection points. First of all, are there any asymptotes or holes? No, done. Doesn't go on my sign chart. I'm going to put my sign chart down here. The minute it says inflection, I know this is a question about the second derivative or about concavity changing. I take the first derivative, and I get a negative 6x squared plus 12x. Again, if my question was about critical points, increasing or decreasing, or extrema, I would analyze my first derivative on a sign line. But this is about inflection points, which is where concavity changes. So I'm going into a second derivative. I want to find where that second derivative is 0 or does not exist. It exists everywhere. The only possible inflection value that I have is at 0. It's not an asymptote and it's not a cusp either. So if I change signs right here, I know it'll do so smoothly from concave up to concave down, or from concave down to concave up, or perhaps the sign doesn't even change. But to determine that, I have to test a point. I'll test my favorite point over here, negative pi. If I put that in there, I've got a negative times a negative, which is a positive. This tells me since my second derivative is positive, I'm concave up there. When I go test my favorite number over here, phi, and I put it in, I end up having a negative times a positive, which is a negative. What that tells me is there was an inflection point. This 0 is called a possible inflection point, but it passed the test. It was in the domain of the function, so it wasn't an asymptote, and the concavity changed. So I would say that G is concave up on negative infinity to 0. Did it ask for inflection value? Oh, it didn't ask me concavity. It says inflection point. So I would say that 0, comma. Now when it asks for the inflection point, it needs a point. 0 is called the inflection value. The 0 being put into the original function would be at 0, negative 3. We'd say 0, negative 3 is an inflection point. And if it's at explain or justify, we'd say because G double prime, and you don't say because G double prime equaled 0 there, because again, it's possible for it to be positive and positive. What it would look like is concave up and then concave up again. So we have to say because G double prime changes sign there. And that's the end. You can go take the quiz, or maybe you took it while you were watching. Have a good one.